Okay, so now I want to look at problem 5.28. I'll do a screen share real quick and let you get your brain wrapped around it. Okay, so we just did this one or most of it. So this is the one we want to look at. There's a lot of little details in here that are worth focusing on. I think this is kind of the last piece of chapter 5 to truly understand it. All right, so pulley problems. Let me see if I can make that a little bit lower. And there's a lot of parts here. Okay. Always good when there's parts A through L. Sheesh. A lot of these are actually very short, though. Okay, in this case, imagine you have a pulley here. Or in my case, I have two pulleys. And there's a light string that runs between them. I'm going to put a mass here. I'll call this one number 2. And then down here, I'm going to put a mass 1. Okay. Now, in this particular case, I'm going to make a coordinate system here, and let me show you a cool trick. I alluded to this earlier in the day where I said sometimes we're going to start with the normal coordinate system. So let's start with one right here. This is an important trick to know. And when I release this thing from rest, this one is going to accelerate upwards, and we'll call that acceleration magnitude 1. Now, when I let go of this block, right, let's assume 2 is heavier, it's going to fall down. Watch what I do with my hand. I'm going to pretend my hand is the coordinate system, right? So there it is. So now I'm going to let my hand follow the string. If the string bends, I'm going to bend my hand. So this is still the same coordinate system. And then let me get over here. And so right here, this coordinate system looks a little bit different, but I want to point out, if I could do this in one sweeping motion, this way is basically clockwise, right? And so what I'm saying is clockwise is the positive direction. So if I just kind of put these little coordinate systems on here and let you see it as I go around. We're setting ourselves up to understand circular motion better. So I'm going to say Y is down and X is to the left. But the reason I'm doing that is because acceleration 2 and acceleration 1 now both go in the same direction, positive Y. We all know that coordinate systems shouldn't affect the answers. So even though it looks weird, this is fine. And I will go into why it's nice to do it this way. Now, inside of this thing, let me see, what else did I label on here? Okay, so there's going to be a scale here. There's going to be some tension. Tension 1. There's going to be a tension over here that we could measure with the scale. I'll call that tension 2. All right. And so it turns out a lot of things are going to simplify very soon. This looks very scary, but part of this question is to learn what we can simplify and what we can't, and what we require in our assumptions to do those simplifications. So, all right, let me see if there's anything else I got to say about this before I start cruising. Okay. So we're going to assume that the scales which read these tensions are negligible. And we're going to assume that the string is massless and inextensible. So I don't know if you've heard that word before, but inextensible, all that means is cannot be extended, right? So that means not stretchy. So if you used bungee cord, that would not be a good model. If you had used thread, thread is usually fairly inextensible because it might stretch a little bit, but not a lot. Or if you used a steel cable, it's not going to stretch much at all. So depending on what type of string or cable you use, we could actually say it's inextensible, meaning it doesn't stretch much. All right. So now, in the interest of time, I guess I better start going through this part. Okay. So I think the first parts are just, yeah, let's just talk about it. I'm going to assume, so part A says, assume A1 equals A2. Now, to be clear, remember, these are the acceleration magnitudes. So what I'm saying is, I think block 1 should accelerate up with the same magnitude that block 2 accelerates down. Okay? So what are our assumptions that make that valid? Okay? And so if we look here, give me just a second. If I'm going too slow, you could always read the solutions, I guess. Okay. What do you think? Why is it okay to say that? Does anybody know what word's in the problem? There's one key word. It's that inextensible. So think about it like this. If this string could stretch, this side would probably stretch more than that side, and they might not be moving at the same rate. If the string can't stretch, well, if this one moves 1 inch, so does this one. So that's why this word is sometimes seen in physics statements. An inextensible string. All right. And then what's the next part? We're assuming acceleration is constant. All right. So just to speed things up, I'll just tell you why. In this case, it's the mass of the string being negligible. Now think about this. Imagine if I used a really heavy chain here. Well, as some of the chain goes over to this side would suddenly weigh more, and it would accelerate faster and faster and faster. So if the string has a negligible amount of mass compared to the blocks, as the string goes from one side to the other, we get a negligible change in mass on one side or the other. No big deal. So here, that's because string has negligible mass. Okay. And then finally, the last critical assumption always used in this one is that we're going to assume that the string tension is the same on both sides of the string in terms of magnitude. We're going to assume that the tension here is the same as the tension there. In the real world, that's not always true. It relies on an assumption. Okay, so this is always true if the pulleys have no mass or the mass of the pulleys are negligible. And I guess we're also assuming they have negligible axial friction as well. Okay. We're also assuming that the string doesn't slip on there, I guess, but I don't know if that would matter to this or not. I haven't thought it through. But these are usually the big assumptions that we make. Now, I don't know which of you plan to be engineers, and you may have, this, you may find this interesting or not, but typically an engineer, when you transfer, one of the first things every engineer has to do in every physics problem, or sorry, every engineering problem, is write down what they are assuming. And the reason you do that is if somebody tries to use your calculations, you need to tell them, hey, my calculation will work as long as these assumptions are valid for your work. And for example, what if somebody wanted to do the same exact problem with a bungee cord? You'd say, that's fine, but don't expect my model to be accurate. Or if your string is very heavy, you'd say, well, that's fine, but don't expect the acceleration to be constant. And finally, yeah, if you have pulleys with friction, don't expect this tension to equal that tension. All right. So, yeah, those kinds of things. So any questions about those assumptions? All right. The only reason I'm spending any time on this at all is we're going to assume until chapter 10 that we always have an ideal string, and we're going to assume that we always have ideal pulleys. So in this chapter and the next, every time you see a string and a pulley, you can actually skip right to this. You could say this is acceleration and this is tension. This is the same tension and this is the same acceleration. This is a tremendous benefit to us in terms of not needing so many subscripts. Again, because of this crap, that's what allowed me to erase the subscripts 1 and 2 here. That's it. Assume that is going to be true for all problems in this chapter and the next. Not true in chapter 10 or some later problem. Okay. All right. What else should we do here? Okay. So now we could draw the Fbds. All right. So here, I'm going to squeeze it in here. This is bad form. Normally I would fit it somewhere else, but I'm running out of room. So I'm going to do the Fbd here. And I want to point out there's going to be a tension up. And there's going to be M1G down. Okay. Over here, there's going to be tension up and M2G down. And I deliberately tried to accentuate this a little bit. If it's going this way, I think this makes sense. If this one's accelerating up, tension should be bigger than mg. If this one's accelerating down, mg should be bigger than tension. And so in this case, I tried to draw them a little bit to scale. Now, we again assumed that the tension should be about the same on each of these because it's the same string and these pulleys have negligible mass. All right, so in this case, take a second and write the force equations how you think they should be. Again, here's the coordinate systems you have to use. I'm going to do it down here and I'll keep it hidden from you. You guys write what you think. Let's see. Okay. Hopefully that was enough time. I'll give you just another 30 seconds, okay? So got 2 minutes left in class. Okay. Here's what I said. So notice the following. This one, Y is up. Tension is positive. Mg is negative. A is positive. T is positive. Mg is negative. A is positive. Now let's go over to this side. Now down is positive. So Mg is positive. A is positive. And T is negative. Mg is positive. T is negative. Ma is positive. Check this out. If you viewed this as a system, tension is an internal force. When you stack the equations and add them, tension drops out. We get M2. Whoops. We get M2G minus M1G equals M1 plus M2 times the acceleration magnitude. Oops. There we go. And from there, we could actually factor out a G, do a bunch of stuff. Let's see what the answer looks like. So if you do this one, there we go. Notice you get the acceleration is this interesting result. Let's go back here. We've got just enough time. Let's finish this out. I know we're running out of time here. But the idea here is we find out that the acceleration is equal to G times M2 minus M1, all divided by M2 plus M1. So that's just by doing algebra on these equations down here. You basically divide through, factor out, blah, 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 blah. Think about this, everybody. Let's see if this makes sense. If mass 2 is bigger than mass 1, you get a positive number up top and it accelerates this way. If mass 1 is bigger than mass 2, you get a negative acceleration. It goes this way. What's something else we could check with every physics answer? Check the
units.
Well, this should be meters per second squared. This one is meters per second squared. And this, if I put in kilograms, I get kilograms over kilograms. They drop out. The units work out. If you used grams, you get grams over grams. They use that. Let's think about this. What should happen in the real world if these two masses are exactly the same? If they were exactly the same, how much would this thing be moving around when I let go of it?
It'd move around until it balances out. Right?
Well, if they're exact, let's say this one's just off the ground here, right? So if this was 5 kilograms and this was 5 kilograms, would it accelerate rapidly or not?
They wouldn't move at all.
Exactly. And that's what this says too, right? Now check this out. What if I put a piano on one side and a taco on the other? You know, the old classic piano taco Atwood's machine experiment. If you put a piano here, wouldn't this thing basically fall straight down really fast? So, well, let's look at that. If mass 1 was really small and mass 2 was really big, notice this mass 1 doesn't matter at all. The numerator and denominator cancel. It falls at rate g. That's like free fall. And notice if mass 1 was really big, you'd get a negative g, and it would be free fall the other way. So if you had a piano and a taco, the piano would fall down. All right, so let's call that good on this one. I think we're probably going to want to do 1 or 2 more problems of this next time and then move on to chapter 6, but or maybe even spend all day next time just doing more examples of this. So Monday is our last day to do this chapter, and then next Wednesday will be your quiz. All right, I'm going to